Space, the final frontier, for a reason. It presents some of the harshest conditions a human could be exposed to, and as such, presents a complex material science challenge to make humans survive. Historically, space exploration has advanced technology and society on Earth, so exploring space will continue to improve our society. Additionally, it provides us with information about where we came from and how the universe works, and space is cool. Since space is a vacuum, and humans typically fare poorly in such circumstances, a spacesuit must contain air and be airtight, survive the pressure differential, and hold pressure to a normal range. This balloon demonstrates the importance of maintaining normal pressure. Temperatures ranging from a nippy negative 150 centigrade in the shadows to a positively toasty 100 degrees Celsius in the sun mean that the suit must be thermally insulated from heat and cold. The suit also must not be damaged easily by debris or abrasion, and as such it must not tear or corrode when exposed to the debris, chemicals, and high-speed impacts in space. Finally, the suit must be flexible. A steel pressure vessel could accomplish everything else, but studies showed that humans are not very productive while in iron lungs, exacerbating all the other problems. Therefore, the materials chosen to create the suit must be tough, puncture-resistant, flexible, thermally insulative, and strong. It doesn't take long for anyone with even the feeblest grasp on reality to realize that one material is not going to be able to meet all of the challenges posed by space. Thus, the solution used by NASA to solve these problems are composites and combinations of composites. For each requirement, there is a different material. To protect against pressure changes, the pressure bladder, which is the inner layer of the spacesuit, is made of neoprene-coated nylon and urethane. Urethane has a low heat resistance and a melting point of 50 degrees Celsius, so it is very crucial that there is thorough insulation to prevent slight issues with the structure and processing of the urethane, such as total melting. Another important piece of the suit is multi-layered aluminized mylar. Mylar is a transparent polyester film with high tensile strength and electrical insulation, which, when coated in a thin layer of aluminum, provides thermal insulation for the astronaut. This layer of the suit serves as the thermal micrometeoroid garment liner and prevents overheating when astronauts encounter direct sunlight. In order for astronauts to remain safe against dangerous space debris, a harder outer shell of Teflon-coated glass fiber beta cloth is used.
The pressure bladder is made of nylon coated with urethane, surrounded by nylon neoprene composite. The urethane is non-permeable, so it holds air in. However, the urethane has very low heat resistance and has a dangerous melting point of 50 degrees Celsius, which would cause problems when encountering direct sunlight. The nylon adds strength, something the poor balloon needed, with a yield strength of 30 to 55 megapascals, which compares with the tensile strength of 44 megapascals for urethane and about 15 megapascals for neoprene. Also, the nylon neoprene composite protects the suit from excessive heat due to its rubber-like structure. This structure is not altered by the temperatures that would be encountered in space. The nylon neoprene has great resistance against rips and tears and is able to stretch, which is crucial for the survival of the humans and balloons in space. The inner layer of nylon functions to hold the air in, and the outer layer includes neoprene to act as a thermal insulator to protect the urethane.
Aluminized mylar is used as a middle layer in the spacesuit for thermal insulation and protection against serious sunburns. Mylar is a brand name used to save time for biaxially oriented polyethylene terephthalate BOPET. The name Mylar is so good at its job that it is estimated to save 1 minute off this video's runtime alone. In its pure form, Mylar is a clear film, very bad at preventing sunburn. However, its application to spacesuits comes in the form of aluminized mylar, a metallized film. The process of aluminization is completed by heating the aluminum inside a vacuum chamber to the point that vapor pressure is formed, causing the aluminum to evaporate onto the surface of the mylar film. The thickness of this coating ranges from angstroms to microns. This gives the mylar the appearance of tinfoil and the added properties of increased reflectivity and impermeability to light, water, and gases. Aluminum has a tightly packed, face-centered cubic structure, which is what keeps light and gases from permeating it through diffusion. The face-centered cubic crystal structure is made of a unit cell of 4 total atoms, with 1 at each corner and 1 in the middle of each face. The The aluminized mylar additionally has high tensile strength, low density, and the ability to be heat sealed, all of which make the material ideal for use in thermal insulation. Due to its high reflectivity, the aluminized mylar can reflect up to 99% of light and reflect up to 90% of body heat back. In spacesuit designs, 4 to 5 layers of aluminized mylar are necessary in order to increase the effectiveness of the thermal insulation. Aluminized mylar's low density makes it a lightweight material, which allows for multiple layers to be used in suits.
The outer layer of the suit is NASA's own Teflon-coated glass fiber cloth termed beta cloth. Beta cloth is a material made of woven silica fibers impregnated with polytetrafluoroethylene, also known as Teflon, another star time saver. The silica fibers are similar to fiberglass and are formed by fusing silica with minerals containing oxides, and the composition is rapidly cooled to prevent crystallization and formed into glass fibers through the fiberization process. The silica fibers are processed by layering woven fibers and cutting the shape desired for the outer layers of a spacesuit. Teflon added makes the cloth extremely durable and able to withstand tears. Teflon is added to the silica fiber material by first coating the silica with a primer and then implanting solid PTFE particles in the primer layer while the layer is still somewhat tacky and able to trap the particles. The implanted particles then serve as anchor points for more layers of PTFE particles to be attached through the sintering at temperatures between 350 and 400 degrees Celsius. Beta cloth is used in spacesuits and as astronauts find it more comfortable and stylish and permits freer movement than the previously used material, nylon. It has a sleek, white and opaque look, not out of place in top fashion designs. Beta cloth is applied in spacesuits because it has atomic oxygen resistance in low Earth orbit, meaning it withstands corrosion. It serves as a tough outer layer with a tearing strength of 2,100 to 2,700 grams in a pendulum tearing test. Beta cloth is fireproof up to temperatures of 650 degrees Celsius, which is the point at which it will begin to melt. These properties of beta cloth make it suitable for spacesuit application as it can withstand the high temperatures and variable conditions present in space travel.
Given the path we are on with global warming, space travel to other planets, Mars in particular, has gained momentum and will require a new generation of spacesuits suited to the unique challenges of Mars. Firstly, a planetary mission requires astronauts to be able to walk comfortably over rough terrain as they can on Earth, and to collect samples, which means more mobility is a must. Secondly, the suit must not weigh as much as past iterations, because Mars' gravity will not lessen the weight very much. Finally, abrasion resistance is essential because Martians never clean their rooms, and Mars therefore has frequent, powerful dust storms, which will destroy a weak suit. For the most part, the materials will be similar, but they will be laid out in a new, totally awesome way. NASA's latest iteration, the Z2 suit, reflects these new priorities with a full soft suit for the limbs and a hard upper torso to add strength. As yet, the materials are undisclosed and in testing, but it is likely that the materials will remain similar.
In conclusion, space is and always will be a complex materials challenge that highlights the use of composites and blending structures to achieve desired properties. As a society, we can all benefit from the information garnered from space exploration and research and the new path for humanity it can provide. As we move towards Mars and other new horizons, the specific materials of the spacesuits will evolve, but material science will constantly play a vital role in the development and testing of the suits that take us there.